Elon Musk just flipped the script on the entire auto industry. The 2026 Tesla Model 2 has something no one expected to see, especially not in a budget EV. A 0.9-meter gap in the chassis. Yeah, you heard that right. A massive structural gap where most cars would have solid metal or welded joints. Some people are excited, others are seriously concerned, and a few are asking the big question: is this a genius breakthrough or a disaster waiting to happen? But remember what Musk promised: not just a revolution in how cars are designed but how they're built. And as with every revolution, it brings some controversy. This strange gap has sparked one of the biggest safety debates Tesla's ever faced. Today we're diving straight into the engineering behind it. And spoiler alert, it turns out this futuristic, stitched-together chassis might just be stronger than any old-school frame you've ever seen. If you're curious about what really makes the Model 2 so different, and how it could change everything you thought you knew about vehicle safety, hit subscribe right now and join the other 999 of us who never missed the real breakthroughs. Let's jump in. So why did Tesla ditch the traditional welded frame and go all in on mega casting? It's a huge shift. But the real answer lies in something almost no one considers when buying a car, yet it could literally be the difference between life and death. Here's the truth the auto industry doesn't like to talk about. Most vehicles on the road today are made from around 400 stamped metal parts, all welded together with over 1,600 separate weld points. That's 1,600 places where things could go wrong. Imagine every weld as a tiny weak spot. Doesn't exactly inspire confidence, does it? And here's where it gets worse. Each of those welds carries a failure risk, somewhere between 0.5% and 1% under extreme stress. Multiply that across a full chassis and suddenly you're looking at hundreds of potential failure points in a structure that's supposed to keep your family safe. It's scary when you actually break it down. Plus, all that welding takes time and money. We're talking 2 to 3 extra hours per vehicle just for welding, and that adds $500 to $1,000 to the cost of every car. That cost doesn't disappear. It shows up in your final price tag. So Tesla made a bold move: forget the traditional playbook and build something smarter. Something stronger. And that's where mega casting comes in. Instead of assembling hundreds of pieces, Tesla uses enormous 6,000 to 9,000 ton gigapresses to create massive one-piece aluminum castings for the front and rear of the car. These are huge structural parts, nearly a meter across, made as single solid components. This reduces hundreds of welded pieces down to just a few major castings. Assembly time drops by 30%, and costs fall by up to 40%. That's how Tesla can even talk about a Model 2 priced under $25,000. The math only works because this manufacturing method slashes about $5,000 to $7,000 off the production cost of each car. Now let's talk about that weird 0.9-meter gap. It's not a mistake. It's the most important part of the design. The front and rear castings don't meet directly. Instead, they're connected by something just as important: the structural battery pack. This rigid pack isn't just for storing energy, it acts as the backbone that ties the front and rear ends together. So that 0.9-meter space? It's actually where everything locks in and forms a single solid structure. Instead of 1,600 weak welds, you've got just 3 main structural connection points. But these aren't normal joints. They're engineered to handle way more stress than traditional welding ever could. Let's talk numbers. A typical welded underbody built from 400 parts weighs around 270 kilograms. Tesla's mega cast design cuts that down to just 198 kilograms. That's a 27% weight reduction, which means better performance, more range, and fewer things that can break down over time. Losing 72 kilograms in structural weight isn't just about being faster. It opens up a whole new world of possibilities for EV design. And it makes electric vehicles far more affordable for everyone. That's the real impact. When you combine these savings with tax incentives, the Model 2 could end up costing less than $25,000. Suddenly, owning an EV becomes realistic for millions of families who've been priced out until now. But now I've got a question for you. If you found out your car was held together by over 1,000 tiny welds, would that make you feel safe? Or would it make you nervous every time you hit a pothole? Drop a comment below with your thoughts, and type the words mega casting so I know you're following along. Now let's look at how strong this 0.9-meter connection actually is. You might be thinking, wait, fewer joints means less strength, right? That's what we've always been told. But Tesla's proven that's not necessarily true. In fact, the real problem isn't too few joints, it's too many bad ones. See, Tesla developed a proprietary aluminum alloy that blows traditional automotive aluminum out of the water. It delivers a yield strength between 140 and 175 megapascals, compared to just 90 to 120 for the standard stuff. That's a 40% jump in strength. And instead of thin welding beads just a couple millimeters wide, Tesla bonds these castings using aerospace-grade adhesives and ultra-high-strength bolts rated at over 1,200 megapascals. That's more than enough to hold aircraft parts together. Literally. Each joint is clamped together with 15 to 20 tons of force. That's like pressing them with the weight of a fully loaded semi-truck. The bond spans 2.7 square meters. That's over 1,000 times more surface area than traditional welds. So when crash forces hit, they're distributed across a massive area, not just tiny welded spots. And this has real-world benefits. Tesla reports that the Model 2 has 30% greater torsional rigidity than the Model 3. That means the chassis is significantly better at resisting twisting and warping under pressure. The total chassis weight also drops from around 225 kilograms with steel down to 180 kilograms. That's a big deal, not just for performance but also for handling and emergency maneuvering. Less mass means less force acting on the car during sudden moves, which improves safety. From a manufacturing perspective, it's night and day. Traditional stamping and welding takes about 6 hours per chassis. Tesla's mega casting cuts that to 10 minutes for the front or rear section. That's a 36-fold improvement. Think about what that means. You're not just getting a cheaper car. You're getting one that's safer, lighter, and built to higher standards than most vehicles today. When a crash hits that 0.9-meter connection, it doesn't snap. It holds, because it's engineered to spread out the impact across square meters of reinforced material. That's why legacy automakers are scrambling to reverse-engineer Tesla's tech. They know welding is becoming obsolete. And now I want to know, does this make you feel more confident riding in a Tesla? Let me know in the comments. And if you're really following along, type 0.9 meter below. Let's take this one step further. Can a stitched-together chassis actually be stronger than solid steel? The phrase sounds sketchy, right? Stitched together. But it's not what you think. Tesla's method uses bonding materials with a shear strength of around 30 megapascals, the same stuff used in aircraft fuselages flying at 35,000 feet. Combine that with ultra-strong bolts and you've got joints that are literally stronger than the metal around them. The castings are aligned using laser-guided systems with micron-level precision. That means zero-stress hotspots, unlike traditional welds that often crack under load. Here's what Tesla's testing found. The Model 2 chassis hits 35,000 Newton-meters per degree of torsional rigidity. That's a 30% jump over the Model 3. Translation, it holds its shape better in a crash. And they've tested it hard. Over 40,000 virtual crash simulations and real-world impact tests at 64 to 72 kilometers per hour. The Model 2 absorbed 25% more crash energy than the Model 3 and reduced cabin intrusion by 15%. This isn't a patchwork. It's a fortress. The structural battery adds another 10,000 Newton-meters of stiffness. That's like adding a steel beam running down the middle of your car. Tesla even based the design on biomimicry, modeling it after the human spine. Rigid sections joined by strong, flexible connections, just like how your body protects itself. Here's a wild test. The Cybertruck, built using this same tech, took on off-road hits at 50 kilometers per hour with zero structural damage. If that monster can handle abuse like that, imagine how the Model 2 will handle real-world road dangers. And for maintenance? Mega casting is a game-changer. With fewer parts, annual maintenance costs drop by up to 30%. Repairs are faster and cheaper. Minor damage costs $200 to $500 instead of over $1,000, thanks to modular aluminum welding. And no more complex frame rebuilds. Tesla just swaps out the damaged casting if needed. This is a car built to last, not fall apart. The 0.9 meter gap isn't a weakness. It's the smartest part of the design. So now you know the truth behind that shocking structural gap in the Model 2. It's not stitched together to fail. It's stitched together to protect and save you money while doing it. If this breakdown helped clear things up, drop a yes in the comments. And if you want to be part of the next major reveal, hit subscribe and let that bell keep you in the loop quietly. You don't want to miss what's coming next.